So we are now recording. All right, so the materials that I'm going to go over right now are basically these three sets of slides that I have that I always use. I'll cover these three sets between today, and it's a lot of materials. I don't want to cover all of it. It's too much. So I'll cover some of it today, and then I'll cover the other half next week. Okay. So let's start with these slides here. So these are just kind of summarizing a few of the ideas. So I'm going to download this. I'm going to start it. All right, so here I'm just going to do a summary of some of the concepts that we have covered in class. Some of the ideas, okay? So basically, machine learning, right? The whole pipeline involves data sets, as you know, right? So data sets are central to machine learning, right? So that's really the main source. We have looked at various data sets, regression data sets and classification data sets. The machine learning algorithms are very data hungry, okay? So whenever you want to build really powerful AI models based on machine learning, they have to have tons of data. Now, the Scifar-10 or MNIST, which have about 60,000 samples, are very small data sets, right? When you're talking about actual AI models, you're talking about really large amounts of data in the millions of examples. So the algorithms are basically defined as being data hungry. So what is better to have? The most powerful machine learning algorithm and small amounts of poor data or lots of data, even if our algorithm is not the best.
Good data?
Good data. Data is king, right? As it says there, data is king, right? And that's really important, okay? So if you might ask yourself, why have companies like Facebook, Google, etc., why do they do so well?
They have all the data.
Not only do they have all the data, they have good data, right? Why do they have good data? Because all of you that have social media, I bet all of you have at least some social media account, right? And you're always liking and subscribing and writing text and all that stuff. You know what you're doing? You're creating a data set for free with your own personal information and giving it to them. And you're happy to do it. So think about it, right? So that's basically why they do so well. They have tons of really high quality data, okay? So basically, you give them new data all the time and you even annotate it for them by labeling it with likes. So you say, or you say, oh, I like this beach, I want to go there. Already you're giving them so many things, labels basically, that then they leverage for the future. So we talked about characteristics of data sets. So I'll just remind you, rows and columns. You should all know this by now. Know how to index matrices, etc. So we've talked about that, and you know this. So we talked about the iris data set last week, I believe, right? And so, or some time ago, right? I confused the two sections. And so basically, I remind you, there's three labels: setosa, versicolor, virginita. So that's 4 features. And then, it's got 4 features, and then it's got these 3 classes. And the X matrix is 150 by 4, and the Y vector is 150 by 1, right? So don't forget about that. So right now, I'm just kind of summarizing. Now, a lot of the data sets that we've looked at have been, basically CSV type of data sets or image data sets, but we also have other data sets like text data sets, right? So you have sentences, etc. And you might wonder, how do you go from text into feeding it into something like a machine learning algorithm? Because we have to convert it into X. That never changes. So how do we do that? So that topic, it's the last topic this semester, which will be covered around transformers, right? And it's, yeah, go ahead.
I was looking into that. I don't, not that I could do it, but isn't it through a process of giving all the different strings of text and letters tokens and values?
Yes, exactly.
Making vectors.
Making vectors, you're right. You create a vector. And so if you have 100,000 sentences, that's each one of those is a row. And then what are the columns? So in the past, you used to use something called the bag of words approach, where basically you just had each word out of 70,000 very frequent words, and you would say yes or no, it's present in the sentence. But that creates a matrix that is 100,000 by 70,000, which you should be convinced that it's pretty large. And also, it's basically zeros. Anyone, if you ever look at it, you're literally, you may find a section is just zeros. And that is called a very sparse matrix. And there's a whole area of math on just sparse matrices. That's not great or not ideal for machine learning. So what we do nowadays is we don't want sparse matrices. Instead, we want dense, very full matrices. And that's what Lenny is getting at, that we convert them into vectors. So you literally say, you know what, I want all the sentences to be of size 256 and no more, not 70,000, 256. Think about how much we shrink it, right? And so how do you do that? That's the key question, right? And so that's actually where autoencoders come in, which is a technique. It's basically like compression. You're going to find some algorithm that is going to achieve that goal. Given sentences, output vectors of size 256 that are dense, full of values. Do you see that? So that's a technique called autoencoders. And as I said, there's algorithms like word2vec, etc., and more that do that. And transformers take advantage of that idea as well. So those are all concepts, as I said, that I'm going to save for the transformers section. But at the end of the day, we do want to arrive at this X matrix. And nowadays, it's actually pretty straightforward because there's techniques called sentence piece or other techniques that actually just do it for you. And that tokenization part, but it's very important, okay? All right, so anyway, so text is, when we get to transformers, we'll touch on that subject again. Images data set, so we've looked at this, that's SciFar and MNIST. That'll pretty much be the whole content of images for this semester, except when we do the GANs, as I said, where we'll do MNIST again, and we'll generate some images, and you know, that will cover those ideas. It's kind of nice because GANs use autoencoders, so it'll lead us in to autoencoders and transformers, and so there is a connection there between the two. And there's other data sets, such as for network intrusion, so like if you have packets or something, but at the end of the day, you're making everything into this X and Y matrix and vector. What are features? Again, these slides are just summary, so I just want to make sure that all these topics are covered. What are features? They're ways to represent a sample. A sample is usually a row, and the columns are the features. And they create what is called a vector space, right? So if I have Iris, it's got a vector space of size 4, correct? That means there's 4 axes to it. So let me do this with my pencil here. Right, so if I have 4 features, then that means it's called R4, and that translates into a space that we know a space that looks like this is being 3-dimensional. Because it's 4, it would have to have, sorry, I couldn't see the thing. Okay, it would have to have 4 dimensions. Keep in mind, they're all orthogonal, which means, it's a fancy term, just means 90 degrees. In geometry, 90 degrees, but because you know these are hyperspaces, you use the term orthogonal, but it basically means the same thing. And why is that important? It means they're independent. Why? Because this cannot project to this one, but if this one was like this, then it's got a projection to this vector. And the implication is that they're not independent, okay? So that's why they need to be like that, 90 degrees. All right, if we talk about MNIST, it's got what, 784 sample features, correct? So the space is R784, and that means that we have literally a space of 784 ... orthogonal axis. And this is great because, as you know, you can compare one image to another in this space, right? By taking a Euclidean distance or some kind of distance. Yeah, go ahead.
Is each orthogonal angle the one feature?
Yes, well, each orthogonal axis is one feature. That's a good question. So this would be F1, F2, F3. Why is that important? That's important because then you can do geometric things in that space. So any data set that creates one of these vector spaces becomes a geometric space. You know, Jason is over there, I'm here, I can measure the distance between Jason and me, right? It's like what, like 6 feet or something. Do you see that? So that's the same with MNIST. Even though it's a space of 784 axes, right? If I have a 7 here, and I have a 7 over there, and then I have a 3 over here, I can measure the distance between this 3 and this 7, and this 7 and that 7. Do you see that? And then I can determine which one is closer to it, to, you know, to the original 7. So just remember that idea. You don't have to complicate, you know, think of anything else. Regardless of the size of the number of features, you can create a vector space, right? Whether it's, you know, could be 1,000,000, right? And what's great about it is, just like in a three-dimensional space where you can take distances, you can calculate distances in that larger space and use that to your advantage. That's how KNN works. So whenever we did IBK, that's KNN, we can do it with MNIST, with, you know, whatever, and it works, right? And it's because of that property. Does that make sense? Okay. All right, so that's important concept. That's the vector space model, which I think is an important concept. Types of features, usually they're numbers, as you know, and they are either binary or continuous, right? So continuous is like a number, like, you know, iris 3.5, 3.6, 3.7. Binary is, you know, present, not present. Got it? Now, it's not a good idea to have, for instance, let's say that you have type of vehicle as one feature, and then you say 1, 2, 3, 4, 5, 6, 7. It's not a good idea. Why? Why do you think it's not a good idea? Do you know what I mean? Like a column where that has, instead of being binary, it has 7 values. 1, 2, 3, and type of vehicle. So one might be boat, one might be car, one might be plane. But that's not a good feature to have.
I was going to say it's going to be hard for the model to learn off that.
It might be. Also, because is a boat, which is 7, and a motorcycle, that's 3, somehow is that boat more than that motorcycle? You know what I mean? There's no context for that. Do you see what I'm saying? Or let's say airplane is 2. Why? Why is airplane 2? If anything, it should be 1,000, right?
Yeah.
Right, but we're not even saying that. We're not saying you know, if the device is complicated or simple, right?
We're just giving it a.
We're just giving it a code, exactly.
Yeah.
So it's not a good idea in general to do that, because the machine learning algorithm might start to think, oh, 7, you know, I'm gonna think that's more important than 2, even though it doesn't mean that. Right? So instead, what should you do if you have 7 categories like that in one feature? Simple, convert it into 7 features. Do you see that? And make it binary. So is it a car or not? Is it a boat or not? And then it's kind of a one-hot encoded representation, which you guys already understand that, even though it's in the feature space. Got it? Does that make sense? All right, so as I said, I'm just doing some ideas. Dimensionality, number of features determines dimensionality. I already talked about this. It's R2, R3, you know, R 1,000, 10,000, etc. Right? That's just the number of features which determines the space. And remember, if you have a vector space, you can do geometry in it, and that's useful. So machine learning is essential for automated systems to make decisions and to infer new knowledge. There's basically, we've talked only about supervised learning. That's all we've done. Even though I broke the class into regression and classification, both of those are supervised learning. Why? We have labeled data, right? We don't just have the X data, we have Y data as well. What if you only had X data? In that case, it would be unsupervised. And we have an algorithm for that, k-means. Usually that's an easy topic to cover, so I'll cover it towards the end of the semester. We'll cover the k-means clustering algorithm and go over that one. So I usually do that in one lecture, okay? But we will cover that topic. I want you to know about it. I mean, you know, you can do things with that, okay? Also, there are semi-supervised I guess, approaches, semi-supervised. So it's not supervised, it's not unsupervised. It's called semi-supervised. And this is actually used in large language models, for instance. What does that mean? It means basically this. In a supervised environment, you have to label the data. Like, you have to grab a sentence, read it, and say, funny, not funny. You know, only a human can really do that, right? If you want to have good data, labeled data. But in large language models that receive basically the entire internet, you can't have people reading over things and labeling them, right? That would not work. It's just not possible. But what you do have is that text is already correct. So if I grab a paragraph from a book, you know, Huckleberry Finn or something, I know that that paragraph is correct, right? Within the context of that book, of how it was written for the times. And so what do you know? You know that you have one sentence and the next sentence, they're related, they're correct. And so that what semi-supervised means is that you use that to train models. So for instance, you might want to build a model that predicts the next word. So give it one sentence and the next sentence. Do you see that? Or actually give it one sentence as an input and the same sentence as an output, and then take out a few words randomly and ask the model, fill in the blank. Do you guys see that? Do you see how it's semi-supervised? You just grab text. That's all you have to make. No human has to read the text, and yet it can feed into a machine learning algorithm. This is in fact how BERT models, which are a variation of transformers, work. You just give it the sentence as input and output, and then randomly drop a few words, and then it learns to fill in the blank. Okay, and this is a training technique. Got it? Any questions on that one? Very important, actually. So with supervised approaches, this part you already know about. Within supervised approaches, the learning methodologies can be divided based on whether they predict a class, so these are the classifiers, what we're currently doing, or a magnitude or a continuous value, which is the regression models that we did before, okay? So that's, you already know about that. Also, there are other ways of doing machine learning, like when you have sequential data. Sequential data basically means that you're going to predict a sequence of events. So for instance, I want to predict ice cream. I'm a company that sells ice cream, and I want to measure my ice cream sales based on over 1 week based on temperature, right? So I need to look at what the weather is going to be like: rainy, rainy, sunny, sunny, rainy, right? And then I can predict, okay, ice cream, no ice cream, no ice cream, ice cream. Do you see what I'm saying? Actually, probably the other way around. The other way around, right? So you want ice cream on a sunny day. But yeah, exactly, good. So that's sequential because the model has to predict a sequence of things, and they depend on the previous one. This is also happens in language, right? So if you do language, you know, the car is going very fast or slow, but you're not going to say the car is going very tired, right? Tired, yeah, exactly. So maybe you are tired. So it's not going to say that, right? So that's also sequential, and that's a still done with machine learning. You just have to frame it in a specific way, right? So that's what transformers are for sequential models, hidden Markov models are for sequential models, and RNNs, which have been displaced by transformers a little bit, are also for sequential models, okay? So these are all things. I won't cover RNNs this semester as they have been displaced by transformers, and hence we're going to cover transformers instead. Hidden Markov models is covered in the foundations class. Okay. All right, here's you played with some of these, as you know. This is just a little table that I put together of different machine learning algorithms. We played with support vector machines, decision trees, neural nets, k-means, naive Bayes in Weka, right? So you know how to use them. These are what I usually call the traditional machine learning algorithms, which work, right? In the regression problem, regression trees work really well. Okay. So classifiers are machine learning approaches that produce as an output a specific class given some input features. And here are some of the important algorithms. Okay. Deep learning based methods are simply neural networks with more layers. So you should know that by now, right? So don't forget that. And deep learning methods have made a big impact in the field of machine learning in recent years. Basically, the competition, SciFAR 10, takes you back to 2012, roughly. All right, so that's where you are, like with the class, I'm putting you in 2012, and what was done with, because you're going to use a CNN, possibly, I don't know, to win the competition, okay? Obviously, the CNN that they used for the competition, which was the ImageNet competition, was probably more advanced, more layers, etc. I can tell you one of the best CNN-based pre-trained models right now is called ResNet, and it's got many layers. Okay, many layers. But to build ResNet, though, I'm pretty sure it took like 5 years of experimentation for people to arrive at the current version of ResNet, which is a pre-trained model. And as I said, not that I'm pitching the 530 class, but that's where I cover that. Okay, all right. So anyway. For the competition, I don't want you really to use pre-trained models, right? Instead, let's just stick with writing it from scratch, right? Build your own architecture. You can do research, and if you want to add many layers and things, that's fine. But I would prefer if you're doing everything in PyTorch to practice. Okay. All right. So given enough computational power, they can automatically learn the optimal features to be used in a classification problem. So this is an important concept that I want you to understand because it's going to lead into CNNs, okay? So it used to be that one of the things that I will cover when we cover CNNs formally is filters, image filters, okay? And what does that mean? It means that you take an image and you're going to run it through a filter. You know, filters are called like a low pass filter, a bypass filter, an averaging filter, you know, and yeah, many filters, right? Many filters. So basically what they do is they can create, let's say you have 256 filters, right? So that means that you take an image and you run it through these 256 filters, and now you can get 256 representations of that image for each of those individual filters. And if you have a really good filter, let's say a face detection filter for a face detection problem, it's going to find the features that identify a face. You see what I'm saying? But in the past, as early as 10 years ago, you know, people would spend years creating these filters. That was called feature engineering. And this is what people did. So the pipeline of machine learning was take your data, create some filters, you know, do some research for 5 years, and create 2-3 filters that kind of work, and then process the images, right? That's feature engineering, and then create the X and Y matrix, run it through support vector machines, classify faces, no faces. That used to be the pipeline. People by hand created the filters. CNNs don't do that. Instead, with CNNs, what you do is you kind of have the same pipeline, but a human doesn't have to go in and create these filters by hand. It's impractical. This is where deep learning really helps you out. You let the AI model learn. You let the AI model learn these filters by itself for the task that you're trying to do. So let's say you're trying to do face detection, right? So instead of taking the image and running it through 256 filters that you know about, you really just create 256 filters, which are basically little matrices, right? So you take the original image, you multiply it times another matrix, and you get a new matrix. That's it. Like the NumPy homework that we did, right? Where we multiplied a matrix times another matrix and got yet another matrix. Similar idea. But this time around, instead of you adding the values of the filter, you leave them blank or random. And then what do? You train the model. So as the model is being trained with massive amounts of data, what's happening? Those filters, the values in those filters are actually the weights, part of the weights that you're learning, part of the connections. So you give it an image that has a face and you have a label that says face. And then you give it an image that does not have a face and the label does not have face, right? As it's doing that process, the filters are being filled in. Does that make sense, guys? And that's basically a CNN. So there's a lot of little architecture things here and there, but that's what's happening.
So it makes its own filters based off the problem you give it?
Exactly. Exactly.
Awesome.
And think about this. They're even better filters because you might use an averaging filter, a low pass filter, and those are not relevant for face detection. Whereas you have a specific task, face detection, all filters in there are being updated with the only goal of improving performance so that when you give it an image, it tells you there's a face or not a face. You see that? That's pretty good. And so if you have massive amounts of data in the architecture, you can do that. And that architecture is called the convolutional neural network, okay, which we will cover more formally later. But I wanted to talk really just about feature engineering right now, okay? So people make, so, you know, you talk about like technology displacing jobs, right? That's a job that was totally displaced, right? So people were doing, you know, spent a decade and built like 5 filters, and that was very productive, actually. And then you let a CNN, and in a couple of weeks has discovered 256 filters that are way better, you see? And that's actually, ResNet is this thing where you've now trained it with millions of images, and it's learned general filters for many tasks. So actually what a lot of people do is they use CNNs just to take an image and convert it into better features for the representation. You see that? So the filters can be reused in other tasks, is what I'm trying to say. Not from your CNN that you're going to build for this class, but ResNet, which is a much better trained with massive amounts of data. Those are really good filters, and you can use them in other tasks. And it's been proven in many competitions that they work really well. Got it? Does that make sense? So that's really how AI is leveraged. That's one of the things that I will say, like you saw in the regression competition, actually deep learning wasn't better than regression trees. But where deep learning and AI has a competitive advantage is when you do this kind of thing, like leveraging massive amounts of data and applying it to general things or generative models also. Got it? Any questions? Make sense? All right, so that's feature engineering. So yeah, I have a slide here. Feature engineering: in the past, learning what features to use required using humans to engineer these features, right? So just remember, if you get confused, CNNs before, I had to put in filters and I had to know the values of them. Now CNNs can learn the values in those filters, and that's a much better thing. So this issue has now been alleviated somewhat by deep learning, and it revolutionized the industry in so many ways, okay? That's one of the great things about AI, is just nowadays, we want to let AI solve the problem that we can't solve, right, in some way. Okay. So I've said this: artificial neural networks are classifiers that can handle non-linearly separable data. So we've talked a little bit about that. right? In theory, this capability allows them to model data that may be more difficult to classify, right? Because they don't build linear models, they build like curvy models. Okay. Then these are some of the libraries, so I won't cover this, but you guys have seen sklearn, NumPy, train, test, split, standard scalar, so you're familiar with all these functions. Also, matplot, pandas, and yeah. And then you know how to use train, test, split. We've talked about the random seed and how that works. We even did the poor man's tenfold cross validation. So we've covered that. Okay, this is the last part that I do want to cover, optimization, right? So everything that we do in machine learning is basically optimization, an algorithm that, given some data, tries to achieve some objective, right? And basically tries to optimize something. So before we, we should say something about optimization. So optimization is a key process in machine learning and really the most fundamental thing. This is what you guys are doing, optimization. Basically, any supervised learning algorithm needs to learn a prediction equation, right? So we've seen this many times, y equal mx plus b, except that with neural nets, the equations are much more complicated. So we need to, given an equation, we need to learn some of those parameters. So in the example of y equals wx plus b, what do we need to learn? W and B, right? We did this at the very beginning of the semester. And as the neural nets get more complicated, we have more weights and biases. The prediction function usually has a set of parameters that must be learned. And the question is, how do you learn these parameters, right? And basically the answer is through optimization. So in its simplest form, optimization consists of trying a set of parameters with your model and seeing what results they give you, right? You should be familiar with this. So you have y equal wx plus b. You give it an x, it predicts a y. What do you do with that y? You compare it to the real y, right? And you want the result of that comparison to be what? As small as possible. That's the minimization. So you take that difference, you look at it, and you're like, okay, I'm going to try another one, randomly change W and B, get another one, and then from there you can start to compare the results, right? This is what we would do, but the problem with that approach is that it's not efficient, right? We can't just randomly change the W and the Bs, although this is what we want to do, change them. We have to find a smarter way of doing that, right? And that's what stochastic gradient descent is the algorithm that allows you to update the weights and the biases efficiently instead of randomly. When we have maybe quantum computers and we can just run all possible scenarios all at once, then maybe we won't need stochastic gradient descent, right? We'll just run all and look at whatever is the lowest. But until then, you need an algorithm that does that. Got it? So if the result is not good, the optimization algorithm needs to decide if you should decrease the values of the parameters or increase the values. In general, you do this in a loop, increasing and decreasing until you find an optimal set of parameters. But one of the questions to answer is, do the values go up or down, right? So if you remember, we need to update the weights and the biases, and how do we do that, right? So that's really the key, is figuring out, do we change that W by adding or subtracting? And what we add or subtract is just a little bit of a small number, which we call the learning rate, okay? As it turns out, there are methodologies based on calculus that help you to make this decision, okay? And that's what part of the stochastic gradient descent relies on this idea. So let's take a look at this graph, right? So this graph, if you remember, in machine learning, there are two equations that we always write, right? What are they? The inference function, and the other one is called the loss function, right? We have the inference and the loss. The inference, you can all think of it as the neural network. It's got some inputs, gives you some outputs, some very complex architecture, right? That's the inference functions. In its simplest form, y equal wx plus v. Simplest. But it could be a function made of multiple layers of a neural network, right? That's the inference function. That can be plotted, and that's plotted in the space of the data. Then we have the loss function, which can also be plotted, but in another space. It's not in the same space as the data, and it's in its own space. And that's what this is. This is the loss function plotted, but in another space, not in the data space. Okay, in fact, this space is smaller because really all it cares about is the relationship between the W's and the cost of them. Okay, so let's take a look at this one. See if I can write on here. This is the function for the MSE in regression, which is usually the most intuitive thing to think about. What was MSE? Mean squared error, right? Which had an appearance such as this one, correct? And then we would do like the sum of errors and the average and so on, right? But let's simplify it just to look. I think this is an origin. All right, let me draw it over here. Let's just think of it like this. Sorry. All right, so that's the MSE, right? So we're comparing the predicted to the real, take the difference and square it, right? Why is this J, this thing here, this curve? Why is it? Because if you really think, once you take the difference between the predicted and the real, you end up with some term, call it diff, right? And then that diff is squared. So this is equivalent to just having x squared. And if you think x squared, what shape does it have? It's like that, right? Looks like a bowl. Let me do this in this. It drives me nuts. Sorry, it's driving me nuts. Okay, so let me draw that here in the whiteboard. Same thing, right? So the cost function, this is the cost. And this is just the parameter space, W, right? And then I had something like this. There was a little star there. And then there was a point, and then there was this line, right? So my question is, I'm saying to you, there is the loss function, and then there's the inference function. The loss function has its own graph, which looks like this, right? On one side, we have the cost, which is what? What is the cost? Is doing this. So if this is a bad prediction, cost goes up, right? If it's a good prediction, it starts to go down. So that's what we capture on this side, right? And on this other side, we're just capturing the weight. Why do we capture the weight? Because the weight is in in y hat. Why? Because y hat is w x plus b, but really what determines y hat is this w over here. Do you see that? So basically, as we modify that w, we are modifying the cost. You see what I'm saying? Like if this w is pretty bad, this y is pretty bad, so this loss is pretty bad, so it goes up. But as this w is pretty good, this y hat is pretty good, which means y hat minus y is pretty good, which means this goes down. Do you see what I'm saying? Now, graphically, if you remember your geometry classes, what I was saying is, why does it look like this curve? Because y hat minus y squared is really, parentheses, is really a diff, right? It results in just one variable squared, and that's really, I can change it to any letter I want. Let's say x squared, which is more familiar, and x squared is the quadratic function, which basically looks like a bowl shape. And a bowl shape guarantees what? that there will only be what is called one minimum down here. Do you guys understand this interplay that's going on? And so now that we have this, our objective is to get to this point, right? Let's say that we started out here. Why do we start there? Because we probably picked a W that is random. And if it's random in this relationship, it's not good. So it produces a Y hat that's not good. And then this Y hat minus the real Y produces a bad cost. So that means the cost is high and it's up here. Do you see that? But as you start to improve the W, what's happening? It's going down to eventually a point where you've reached the minimum. Okay? That's how geometrically you can think of all of this. But all of this is the equations ensure that it happens like this. Why? Because our loss is MSE. And MSE is this thing here, right? And that thing has this shape because it's X2. Okay? And then within, it's like a universe. Think of it as, we define that those are the laws of physics of that universe. Sorry. And so now, whenever you change a W, it has to live within that space, right? And so that space is either going to say you're going to go up in this curve or down in this curve. Your objective is to go down in this curve and so that this is the minimum because that's what you want, okay? And so additionally to this idea, there's this other idea of how do we do it analytically? And as it turns out, calculus has a little trick that says, well, grab the function with respect to this W and take the derivative of it. And guess what? It's going to give you a parameter, a result called the tangent to that point. And what that gives you is it gives you a number with a sign, either positive or negative. Do you see that? So that's just math, you know, blame Newton or whomever, right? So you take the derivative of J with respect to the W. And you're doing that for all the parameters. Because that point lives in this function, the function we know is this X2, which is this J. And so every time that you do deep learning, you're taking these derivatives. Every time. Go ahead, Glenn, please. Each epoch.
Up and down.
Yes, each epoch you are doing this. Exactly. It did.
So that's happening on each one of those orthogonalities,
Those
right?
are the data.
Okay.
It's happening in the architecture as you're training. So every time you're training, think about it. Every time you're training, right? You give it some data, you try some weights, you predict this, you compare it to the real, and then you need to update the weights.
Okay.
Based on this information. Got it?
Yeah.
So yeah, so the derivatives, these things are happening every iteration. So if you do this 100,000 times with a data set of 1 million batches of 64, every 64 batches, this is happening. But this is only part of stochastic gradient descent, right? So it takes those derivatives and then it decides the sign will determine how to update the weights and the biases, okay? This is the trick that allows you, because we could do, so what I want you to think is we could do this randomly, just change them randomly, right? But that would take forever to train and we may never find the values. But if we do it in a smart way, we do it like this. So now so for instance, if the thing was here and the tangent looks like this, let's say this would give you positive, this would give you negative. What that means is that the W here is plus what? A little delta, right? Determined by the learning rate. And over here, if it's this one, it would be the weight where it is minus a little delta and a little delta weight, which is determined by the learning rate. But this sign is what's extremely important. And it's given to you by knowing the shape of the function and the W, and then, as I said, taking that derivative, which gives you that important information. And this is why we need PyTorch or TensorFlow. That's what they do. They calculate those gradients, and it's a whole thing. Okay, it's a complicated thing that it does, and it needs to do it efficiently and really fast. All right, and so That's what they provide, the gradient calculation. Okay? Any questions on this idea? All right, so let's keep going. Let me go back to here. All right, so this is the slides, right? Now I'm going to click on it. Okay, there we go. So as I said, I've talked about this. So that was the optimization graph. And I've talked about all these, so you can just read it, okay, for your own information. Now, I provided this nice example. I'm not going to demo it, but go ahead and play with this if you would like. This is in Python, and it's basically the idea. So think here, I have, it's not homework, it's just for your own information. If you look here, this function is called the function derivative, right? So what does that mean? It means that there's some function, and I have to take the derivative of that function and get a new function, right? And I just hard-coded that function here. You see that? And then I'm showing you here how you would update the weights. So basically, if you notice, you're in a loop, you check some criteria, right? And then what do? You update the weights. So you can see the update happening here. Why? Because you have an old X, a new X, and then you do minus or plus, it doesn't matter, right? Because what matters is what this is going to return, which this will have a sign too, okay? And so you do a minus step size times that symbol. Does that make sense, guys? So the step size here might be 0.0001, for instance, right? This is the learning rate that we pick. This old value is just the W, and this is the new W, right? But the thing is, the X goes into function derivative. And function derivative is, as you can see over here, the derivative of some original function. So that means that this would give you the tangent in that function that we're talking about. So for instance, here, I have the original function, right? So in the previous code example, we assume a function x3 minus 3x2 plus 7. So what is the derivative of this? 3x squared. 3x squared minus 6x, right? Okay, let's go back to the function. You see that it's the same function, right? And so basically that's what's going on. This is just me hard coding it. But basically, this function that I wrote over here would be equivalent to your loss function. Do you see that? So you would have the loss function, and you would take the derivative of it. Okay. Well, it's the same thing here. Imagine then that this function here is your loss function. So we take the derivative of it. Okay. So basically that's what we do. So we would convert that one. When you see the divs or the gradients, basically that's what's being stated. If you take the derivative of it, that becomes the new function that you're going to use to update the weights. Okay. And remember, as I said, the important aspect is that it provides a parameter here, a plus or a minus sign to indicate how you're going to update the weights. Okay, so this is the main concept of taking the derivative. So the parameter x can be calculated in a loop using the derivative function, which will determine the direction to follow when increasing or decreasing the parameter x. Okay, so that's going down the curve or going up the curve because it can only do that in the space that we created in the previous graph. Here. Do you see that? So notice W here, either that way or this way, but it can only live in this line. That is its only space in which it can live for this relationship. Okay. So that's the idea basically. So you can play with this code. It should work. All right. Yeah. All right. So that completes these slides. So it's 6 o'clock. And then, as I said, today I just have slides for the first half. I want to cover these, and then we're going to go back to our MNIST code and finish that up. So let me, we got these guys who are taking an exam. So let me just do then.